Okay, now let's talk about how we can process things using diffusion. Process things using diffusion. Now I mentioned that we can, make iron harder by adding in carbon atoms. So that's called carbonization. Or you can call it case hardening. There's lots of different ways of talking about it. It just depends on what you're doing with it. Like for example, in this case right here, if we cut out this edge of this gear, what you see is that on the outside edge there's a difference in the color. That's because it's been case hardened. Carbon has been allowed to infiltrate those sites. So in the center we have more or less pure iron or some sort of alloy. On the outside we have iron with a higher carbon content. It makes it harder. Now there's reasons for this. For one, it helps with improving wear resistance. If the outside is harder, then that gear is going to be harder to scratch and break right there at the edge. Also, there are compressive stresses. I mean, that interstitial atom, it fits pretty well, but I'm not saying it's perfect. It is going to be pushing on the atoms around it. And because of that, it's actually going to improve its resistance to fatigue failure. Now, why would it do that? I'll try to explain in a very simple case. Fatigue failure is when you do something over and over again and eventually a crack forms. Okay? Some sort of crack forms in your object. That's not good. You don't want to crack. Oh, of course I destroyed it. Little Power Ranger symbol here. Go, go, Power Rangers. Now, that's not good. So as you're moving it back and forth, that gets longer and longer and longer. However, I said that there's compressive stress because of those carbons in there. What's happening is we have, atoms are not this big, but I'm having to exaggerate here a little bit. And when we have those carbon atoms in there kind of stuck into it, they are pushing out and saying, I don't like this, you're kind of squishing me, so move away. And because they are pushing those iron atoms, the iron atoms are pushing inward. They're pushing away from the carbon atoms. And that is going to cause them to squish together this crack. When you squish together the crack, it's less likely to grow and less likely to cause it to break. Now this is a very simplified case here, but it's one of the reasons that you very, very, very rarely hear about things failing from compression. Like if you have a column, or let's just say a beam or a rod, it takes a lot more for it to fail from compression than it does for it to fail from tension, because compression closes the cracks. They get squished together, while tension causes those cracks to grow by stretching them apart. So, more you know. Interesting little details here. But this is one of the reasons that we process things using diffusion. Now, another thing we do with diffusion is doping. We dope it. Like semiconducting devices, their performance is often based on a type of impurity. So we will take a type of atom, in this case phosphorus, and we're going to put that on the top of my silicon device. Now I just lay it on top of there, and over time, if we add some heat, will cause vacancies, and that phosphorus will then soak into the surface. It will infiltrate the surface and will have doped it and changed the performance of my chip. This can help it with conducting electricity. It can improve its thermal conductivity. There's all kinds of things that this might do. There's all kinds of reasons we might do this and all kinds of different atoms we might use. What I want to get through today is that all of this is coming from diffusion. We open up vacancies through heat, and then that heat allows the vacancies to form, and then our atoms can then infiltrate into our larger host atoms. Or in the case of carbon, we just make sure that the carbon is very hot and the iron is very hot, so they're vibrating around and it makes it easy for the carbon to infiltrate. So, thank you for listening. I hope this helps you, and I'll see you all next time. Bye-bye.